So hi everyone. So in this class let me discuss some more examples based on convergent and divergent sequence. Okay. So example is, give an example of a monotonically increasing sequence which is convergent and divergent. So we have to take an example which is monotonically increasing sequence. Using that we have to prove that sequence is convergent, and another way another thing is, again we have to take monotonically increasing sequence which is divergent. So here we have to take two examples. One example is two examples. In either case the sequence is monotonically increasing. Using monotonically increasing sequence we have to prove convergent as well as divergent. So consider solution for this. Consider the sequence an where an is equal to n divided by n plus 1. So here put n is equal to n plus 1, then it will become a n plus 1 is n plus 1 divided by n plus 2. That is n plus 1 is equal to n plus 1 divided by n plus 2. So to check monotonically increasing or decreasing, we take so to prove an is monotonically increasing. So an plus 1 minus an is strictly greater than, we have to check it is strictly greater than 0. So here we are taking an plus 1 minus an is equal to n plus 1 divided by n plus 2 minus n divided by n plus 1. So this is equal to n plus 1 square. So cross multiplication, n plus 1 square minus n into n plus 2. So this is n square plus 2n plus 1 minus n square minus 2n. So this n square 2n vanishes, remains what? 1. 1 divided by n plus 2 into n plus 1 is strictly greater than 0 for all n. Okay. Therefore an plus 1 is greater than an for all n. Therefore sequence an is monotonically increasing sequence, because this is satisfying the definition of your monotonically increasing sequence. Because of that reason we are telling an is monotonically increasing sequence. Also I am taking n is less than n plus 1. You take n is equal to 1. 1 is less than 2. Yes. So in general I am taking n is less than n plus 1. So now I am dividing n plus 1 both sides, then it will become n divided by n plus 1. n plus 1 divided by n plus 1 remains what? 1. So therefore n divided by n plus 1 is less than 1. So you know that an is equal to n divided by n plus 1 because we have taken. Okay. Therefore an is less than 1 for all n. That implies that an is bounded above. Here I am taking this as bounded above points. Since an is monotonically increasing and bounded above, therefore it is convergent. That is limit n tends to infinity n divided by n plus 1. So this is equal to limit n tends to infinity n divided by, in denominator I am taking n as common. So therefore it will become 1 plus 1 divided by n. So this n vanishes, remains what? 1 divided by 1 plus 1 divided by n. So if you put infinity, then it will become 1 plus 1 divided by infinity 0. 1 plus 0. This is equal to 1. Therefore an converges to what? 1. an converges to 1. So second thing is, I have to take an example that is monotonically increasing, and using that I have to prove that is divergent sequence. Consider the sequence an is equal to, consider the sequence an where an is equal to n. So in this place put n is equal to n plus 1, then you get n plus 1 is equal to n plus 1. So therefore n plus 1 minus an is equal to n plus 1 minus n. So n plus 1 is n plus 1 and an is what? N. So this is equal to 1. So 1 is strictly greater than 0. Because of that reason we are telling an plus 1 minus n is strictly greater than 0 for all n. That implies that an plus 1 is strictly greater than an. So therefore we can say an is monotonically increasing sequence. But this sequence increases. However, you put the value of n is equal to 1, 1, n is equal to 2, 2, n is equal to 3, 3. So here we can't find bounded above point. Therefore in general I am writing that, also given any positive number k, however large, there exists a positive integer m such that an is greater than k for all n greater than equal to m. So that implies that sequence an is not bounded above. Which sequence? The given sequence an is equal to n has not bounded above point. Therefore, it is not bounded above. Since n is monotonically increasing and not bounded above, therefore it is divergent. So that is limit n tends to infinity n. You know that n is n. So in place of n, you replace the value limit infinity, then you get infinity. Therefore, this is the definition of whether if you put limit in the given sequence, then if it becomes infinity or minus infinity, then the sequence diverges. Therefore, this is the solution for your example. So next example is give an example of monotonically decreasing sequence which is convergent and divergent. Here we have to take monotonically decreasing sequence. Using that, we have to prove one thing is convergent. Again, we have to take a monotonically decreasing sequence. Using that, we have to do it is divergent. So solution for first example, first convergent, we have to check using monotonically increasing sequence. We have to check whether it is convergent or not. So here I am consider the sequence an where an is equal to 1 by n and an plus 1 is equal to 1 divided by n plus 1. N plus 1 is 1 divided by n plus 1. So therefore, n plus 1 minus an is equal to 1 divided by n plus 1 minus 1 divided by n. So using cross multiplication, it will become n minus n plus minus n minus 1. n minus n minus 1 divided by n into n plus 1. n into n plus 1. So this is n into n plus 1. So this is less than 0 because this is minus 1 divided by n into n plus 1. This is less than 0. Therefore, this implies that an plus 1 is less than an for all n. Therefore, an is monotonically decreasing sequence. Also, an is strictly greater than 0. an is strictly greater than 0 for all n. Because in the place if you put, so in an is 1 divided by n. So an is what? 1 divided by n. In this place, put any value of n, means n belongs to n. So an is equal to 1 divided by 1 divided by 2, 1 by 2, 1 divided by 3, means 0.33, like that. That is strictly greater than 0. The value also an is strictly greater than 0. Therefore, here your bounded below point is what? Bounded below point is, means an is greater than 0. Therefore, an is bounded below. Since an is monotonically decreasing and bounded below, therefore it is convergent. Because here we get finite value, that is 0. If I take here limit n tends to infinity, that is limit n tends to infinity 1 by n. So this is equal to 1 divided by infinity, that is 0. Means here we get a finite value. Therefore, the given sequence is convergent. So again I am considering here, consider the sequence an where an is equal to minus n and an plus 1 and an plus 1 is equal to minus of n plus 1. Now check whether it is monotonically decreasing or not. So an plus 1 minus an, this is equal to minus of, so this is minus of n plus 1 minus n. So then this is minus n, this is minus of minus n. So this is minus of minus n. So this is minus n plus n, this is minus 1. Remains what? Minus 1 is less than 0 for all n. That implies that n plus 1 is less than n for all n. Therefore an is monotonically decreasing sequence. An is monotonically decreasing sequence. So your given sequence is minus n. Okay, so for that we have to find bounded below point. Bounded below point. So but here what is happening here, also given also, so if you put any value toward any value of n, so here this sequence is reaching towards your minus infinity. So therefore I write here, also given any positive real number k however large, there exists a positive integer m such that n is less than minus k for all n greater than equal to m. So here we can't find bounded below point, therefore sequence n is not bounded below. So since n is monotonically decreasing and not bounded below, it is divergent. That is limit n tends to infinity an is equal to limit n tends to infinity minus n. So this is equal to minus infinity. If you get minus infinity, then it is minus infinity or plus infinity, that is divergent sequence. Here if you found any finite number, then that is convergent sequence. Therefore this sequence means n is equal to minus n is monotonically decreasing but and not bounded below, therefore it is divergent. So next example is prove that the sequence an where an is equal to 1 divided by n plus 1 plus 1 divided by n plus 2 plus so on 1 divided by 2n is convergent and its limits lies between 1 by 2 and 1. So here solution for this, here let an is equal to 1 divided by n plus 1 plus 1 divided by n plus 2 plus so on 1 divided by 2n. This is given data. So here I am replacing in the place of n by n plus 1. So then this will become an plus 1, this is equal to 1 divided by n plus 2, 1 divided by n plus 3. This is 1 divided by 2n plus 2. Back term is 1 divided, because 1 increasing means so back term is 2n plus 1. So next term is 2n plus 2. If this back term is 1 divided by 2n. This back term is 2n minus 1. So like that terms arranges. So therefore n plus 1 minus an is equal to, so this n plus 2, this n plus 2, n plus 3, n plus 3, 1 divided by 2n, 1 divided by 2n. So remaining term is what? 1 divided by 2n plus 2 plus 1 divided by 2n plus 1 minus this term. This doesn't vanishes with any term of n plus 1. Therefore minus 1 divided by n plus 1. So this is strictly greater than 1 divided by 2n plus 2 plus 1 divided by 2n plus 2 minus 1 divided by n plus 1. So this is equal to 2 divided by, so here we can take 2 as common. So 2 divided by 2n plus 2. That is, here I am taking 2 as common. So this 2 1 goes, remains term is what? 1 divided by n plus 1 minus 1 divided by n plus 1. So plus 1 divided by n plus 1 minus 1 divided by n plus 1, that is 0. Means your an plus 1 minus an is strictly greater than 0 for all n. So that implies that an plus 1 is greater than an for all n. Means an is monotonically increasing sequence. So here we have to find bounded above point. So also an is equal to what? 1 divided by n plus 1, 1 divided by n plus 2, 1 divided by n plus n. That is 2n. So here I am writing this as this is less than 1 divided by n plus 1 plus 1 divided by n plus 1, so on 1 divided by n plus 1. So these are n terms. So this is equal to n divided by n plus 1. So this is less than 1. Means an is bounded above. So that point is 1. Since n is monotonically increasing and bounded above, so therefore it is convergent. Now we write means we have to check whether this sequence have limits 1 by 2 and with 1 by 2 and 1. So now we check that. So now an is equal to 1 divided by n plus 1 plus 1 divided by n plus 2 plus 1 divided by 2n. 1 divided by 2n. So this is strictly greater than 1 divided by 2n plus 1 divided by 2n plus 1 divided by 2n. So these are n terms, n divided by 2n. So means this is equal to 1 by 2. So first we have seen here, so this sequence lies between, this is less than 1, n is less than 1. So here n is greater than 1 by 2. means your sequence lying between 1 by 2 and 1. So hence this sequence lies between what? 1 by 2 and 1. So thank you. So if you have any doubts regarding these examples, you can ask questions. Thank you.